Welcome to Chapter 6, Confidence Intervals. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan. In public health, we often use sample data to estimate what's true in the population, but we rarely get the exact number. Instead, we create a confidence interval, a range of values that's likely to contain the true answer. In this chapter, we'll explore how to construct and interpret confidence intervals for different types of outcomes. First is Introduction to Estimation 6.1. When we collect sample data, we calculate a point estimate like the average blood pressure or the proportion vaccinated. But because we are working with a sample, we also calculate a confidence interval to show the range of plausible values. A 95% confidence interval means that if we repeated the study many times, 95% of the intervals would capture the true population value. Wider intervals mean less precision, and narrower intervals mean greater precision, often from larger sample sizes. Second is CI for one sample, Continuous Outcome 6.2. Let's say we want to estimate the mean blood pressure in a population. We collect a sample and calculate the sample mean. To calculate the confidence interval, start with the sample mean. We use the formula. Then add and subtract the critical value multiplied by the standard error. This gives you a range of values that likely includes the true population mean. If the sample size is large, we use the z distribution. If the sample is small, we use the t distribution. The final interval gives us a range where we believe the true population mean lies, with a given level of confidence. Third is CI for one sample, Dichotomous Outcome 6.3. Now let's say we're estimating a proportion, like the percentage of people vaccinated. We calculate the sample proportion and then construct a confidence interval around that. Take the sample proportion. Then add and subtract the z-value times the square root of the proportion times 1 minus the proportion, divided by the sample size. This tells us the likely range for the true prevalence in the population. It's particularly useful in survey research and disease surveillance. Fourth is CI for two independent samples, Continuous Outcome 6.4. When comparing two unrelated groups, like a treatment group and a control group, we estimate the difference in means. The confidence interval tells us how different the groups are and how precise that estimate is. Subtract the two sample means. Then add and subtract the critical value times the square root of the variance of each group divided by its sample size. If the CI does not include 0, we can infer that the difference is statistically meaningful. Example, comparing average cholesterol between two diet groups. Fifth is CI for matched samples, Continuous Outcome 6.5. Matched or paired samples involve measuring the same subjects twice, such as before and after an intervention. Here, we calculate the mean of the differences between paired values. Then we build a confidence interval around that mean difference. Take the average of the paired differences. Then add and subtract the t-value times the standard deviation of those differences divided by the square root of the number of pairs. It tells us whether there was a consistent and meaningful change over time within the same group. Sixth is CI for two independent samples, Dichotomous Outcome 6.6. We now move into comparing proportions between two groups, often used in clinical trials and epidemiological studies. 6.6.1 Confidence Interval for the Risk Difference. The risk difference is the absolute difference in risk or proportion between two groups. Subtract the proportions from each group. Then add and subtract the z-score times the square root of each group's proportion times 1 minus the proportion, divided by its sample size. For example, if 10% of smokers and 2% of non-smokers develop lung cancer, the risk difference is 8%. The confidence interval helps determine whether this difference is significant or due to chance. 6.6.2 Confidence interval for the relative risk compares the probability of an outcome between two groups. It's the ratio of the risks. Take the natural log of the relative risk. Then add and subtract the z-value times the square root of the inverse of the counts. Finally, exponentiate the limits to return to the relative risk scale. For example, if smokers are twice as likely to develop lung disease, the relative risk is 2. If the CI includes 1, the result is not statistically significant. 6.6.3 Confidence interval for the odds ratio. The odds ratio is commonly used in case control studies. It compares the odds of exposure between cases and controls. Take the natural log of the odds ratio. Then add and subtract the z-value times the square root of the sum of the inverses of the counts from each cell in the 2 by 2 table. Then take the antilog of those limits to return to the odds ratio scale. An odds ratio of 1 means no association. A CI that excludes 1 suggests a statistically significant relationship. For example, an OR of 2.5 with a CI of 1.2 to 5.1 suggests a strong, significant association. Conclusion confidence intervals give us more than a single number. They show the range where the truth likely lies and how precise our estimate is. This chapter covered how to build and interpret confidence intervals for means proportions, risk differences, relative risks, odds ratios, both independent and matched samples. Understanding confidence intervals prepares you for hypothesis testing and critical interpretation of health data. This concludes Chapter 6, Confidence Intervals. Next, we'll dive deeper into statistical testing and p-values. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan.